Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another lecture of our robotics course. In this lecture, we will be discussing about the transformation matrix and also we'll be discussing the concept of pre and post multiplication. Before we go into our today's lecture, let us do some recap of the previous lecture. In the previous lecture, we have already seen how to represent a frame which is not coinciding with the original frame of reference, rather it is shifted and disoriented. For example, let's say we have a reference frame X, Y, and Z, X, Y, and Z, and we have a rigid body which also has its own frame NOA, and basically these two frames are at the moment coinciding with each other. Now let us say I have removed it and put it somewhere else with a different orientation. So the position will be represented with this black color vector, which we denote it as P. Now, mathematically, if we want to represent this new frame, we have to take into consideration the three vectors that describe the directional unit vectors and a fourth vector describing the location. So mathematically, this new frame will be represented as follows. So you have n vector, o vector, a vector, which is this one, and this one. If you bring this here, so this vector represents basically the direction, and also O will represent another direction, A will represent another direction. So overall, it will represent the orientation. And finally, the Px, Py, Pz will represent the position of this new origin. So we can say that this 3 by 3 matrix is basically the orientation matrix. This one is basically the position vector, and the last row is used just to make this matrix 4 by 4 so that the inverse and other transformation becomes easier, which we will see in next few lectures as well. Now, we also have seen in the earlier lecture that let's say this object has been translated to another place without disorienting it further. So in that case, we will have this object translated here by a vector of D, but NOA is still same as the previous NOA, so we can mathematically write down this translation matrix as follows, like this. So this is the dx, dy, dz represents this vector. And because the new NOA is same as the previous NOA, that's why it is basically an identity matrix. Now, how do we get this new frame of reference with respect to the original frame of reference? This can be done by getting this transformation matrix, which is basically a translation, multiply it with the original frame representation, and then you'll get the new frame representation. This one also we have discussed in the earlier lecture as well. So you can see here that this is the old frame of reference, old frame representation, and this is a new frame representation after translation. So you can see this rotation or this orientation matrix remains the same. However, the position vector has been changed. Okay, now let us discuss it in a 2D view so that we can geometrically prove it. So let's say this is a YZ plane and we are not considering the XYZ transformation, rather YZ only. And then this is an OA, another frame, which is two-dimensional. Now I have moved it to another plane. So this is the position vector PY and PZ. Now I have moved it to another place without disorienting it. So it is a new position with dx and dy and dz, sorry. So your new position of this frame origin with respect to the original frame of reference would be py plus dy and pz plus dz. So which is same as the one that we have derived in the earlier slide. Okay, now this is translation. Now let's see what happens if we do the rotation of the frame with respect to its original frame. What will happen? Let's say this is an XYZ frame of reference, which is the original frame of reference, and we have a point P, which is denoted by PX, PY, PZ, and we see another frame, orange color one, NOA, which coincides with XYZ. So basically PX will be PN, PY will be PO, and PZ will be PA because both frames coincide with each other. Now we try to rotate this NOA frame with respect to X with a certain degrees of angle. So then what will happen is basically we rotate it this way. So this frame, O and A axis will be shifted. Okay, N axis will still remain as same as X because we are rotating with respect to X. So this is the angle of rotation of theta. Now, if we see from this side, we want to now derive some relationship such as how is it related with X and N and Y and O and all these things. We will see how to derive it. Now, so to do that, we want to have a two-dimensional view. So we want to basically redraw it with respect to this view. So we will have it here like this. So basically it has been rotated by theta angle, this O and A. So this is the P point. So with respect, so the P point will also be rotated because it is within the NOA frame. So the P point will also be rotated. So PO and PA and PO will remain the same. Okay, now let's do this drawing so that we can derive it quickly and easily. So these are all the theta angle from geometry we can find it. And now let's denote some values to different length. So this is L1 from this origin to this point. This is L3, L4, and this is L2. So this is L4, this is L3, this is L1, this is L2. And also we can see what is PX and PY. So basically this would be PY after it is being rotated. And let's say we talk about this triangle, then we can say that PY is basically L1 minus L2. So L1 minus L2. So from this triangle, we can say that L1 is basically PO cos theta because it's theta and this is PO. So it's basically PO cos theta is L1. And from this triangle, okay, we can see that L2 is basically PA sine theta because this is PA, so we can write down PA sine theta. Similarly, for PZ, we can, so this is basically PZ, which I forgot to mention earlier. So this is PZ. So PZ is basically L3 plus L4. So if you see this triangle, so then we can see that L3 is PO sine theta, whereas L4 is from this triangle, which is PA cos theta. So this is the relationship. We have to note here that Px is equals to Pn because x and n are still coinciding with each other. So the coordinate of Px and Pn will remain the same. Now, in terms of matrix, we can write it down Px, Py, Pz, and this way these equations can be represented by this matrix multiplication as well. Now, for other axes, so this is for the x-axis, instead of cos theta, we write it c theta just to make it shorter in shorthand. So c theta stands for cos theta, s theta stands for sine theta. And if you do the same for y and z axis, you can do the same derivation and you will get different rotation matrix. So these are the three rotation matrix formed with respect to x, y, and z. So this is the theta angle that you have rotated. So our new point Pxyz will be this rotation matrix multiplied by the PNOA, whichever is the coordinate with respect to NOA. So this would be our new coordinate with respect to the original frame of reference after rotating this NOA with an angle of theta. Now, we are discussing still the single rotation. We are still not discussing the multiple transformation. Now, in the convention here is we say UP UTR multiplied by RP. We will see these things very often in our textbook. So let's see what it means. So UP means is the position of the point P related to the original frame of the or basically the universal frame. And then we have another representation P relative to the frame R, which is basically moving or rotating or translating. So in our case, it is NOA frame. So in between, we have the transformation of the frame R, which is the NOA frame, with respect to U, which is basically the XYZ frame. So this is the convention that we use. Okay, now let's do an example. Let's say we have a point with respect to NOA, I suppose, which is denoted as 2, 3, 4 transpose. That means it is 2, then 3, and 4 is basically the position vector, and is attached to a rotating frame. So that means it is with the P is with respect to the NOA frame. And the frame rotates 90 degree about the x-axis. So 90 degree about the x-axis, not theta, 90 degree. So theta equals to 90 degree. Find the coordinates of the point relative to the reference frame after the rotation and verify the result graphically. So let's say you have here the rotation with respect to x. So this is just now we have seen. So here the theta will be 90 degrees. So cos 90 degree will be 0, sine 90 degree will be 1. So we can put all these values and then we can have this Pxy is this transformation matrix multiplied by the original point with respect to the NOA frame. And then we will get the values here. This is basically 2, minus 4, and 3. You can draw it and you can check it graphically. It would be the same as well. Now, but we have said that we are going to use a 4 by 4 matrix. So basically, we can do it this way as well, just by adding this 0, 0, 0, 1 to make it a 4 by 4 matrix. And here there is no translation. So basically, the origin remains the same. Position, so that's why it is 0, 0, 0, both frame X, Y, Z, and NOA. So that's why there is no translation. So we have 0, 0, and 0. And if you do the multiplication, you will end up with the same result. It's just Pxyz equals to 2, minus 4, 3, and 1 is 1. So this is how we can make it a 4 by 4 matrix as well. Now, let's move on to the next slide. Okay. Now, let's say we have another example with translation. Let's say we have a frame that has been moved 10 units along y-axis, 5 units along z-axis from the reference frame, and find the new location of the frame. So we have to first get the translation matrix, which is dx would be 0. Am I right? Or yeah, dx would be 0, and dy would be, dx is 0, dy would be 10 units in y-axis, so 10 units, and 5 units in z-axis, so 5 units here. So you have this one multiplied with your original frame, which is represented by this one. This will be given. This is given basically in the quotient. So this is your original frame. So you do the multiplication, this one, which represent this matrix, the translation matrix, multiplied with your original matrix, which is this one. So you do this multiplication and you will end up getting this one. So you see here, basically, even if you do the multiplication, the orientation matrix will never change because it is pure translation. Only the value of this XYZ will change because you just add the previous position to the current position. So px plus dx, so in this case dx is 0, so px remains the same. In the other case, it is 3 plus 10 and 8 plus 5. So this is how you can get the answer. So these are some simple examples so for you to get familiar with the system. So now we will see the composite transformation. That means not a single transformation, rather a multiple transformation. And here we will introduce the concept of pre-multiplication and post-multiplication. Let's move on. Okay, let's say we want to do a combined transformation. So first, let's say a point 731 is attached to a frame, which is basically a moving frame, FNOA, and is subjected to the following transformations. Find the coordinates of the point relative to the fixed reference frame at the conclusion of the transformations. So now previously in the previous examples we have done only one transform. Either it is rotating with respect to one axis or it is being translated. So now what we are doing here is basically we are first rotating with respect to z axis, then followed by a rotation with respect to y axis, and then followed by a translation with respect to basically the original frame of reference. Okay, now this one you have to understand here. Basically this one, when we say z-axis, y-axis, so this is basically the original frame of reference, which is the fixed frame of reference, and we are doing all the transformation with respect to the fixed frame of reference. And once we do it, we do the multiplication by pre-multiplying it. So this is the rule number one. So when all the transformations are done with respect to the original frame of reference, we do the pre-multiplication. As you know, the matrix multiplication does not commute, so that's why how you put the matrix orders, it will have different answer. So for this case, you have to reverse the order of transformation. So your first last transformation will come to the first multiplier, followed by the second one, and followed by the third one. So basically you go in a reverse order and you do the multiplication to find out your new PXYZ, and this is your original PNOA. So basically you know the rotation with respect to Y is this one and rotation with respect to Z is this one. And then if you put the values here 90 degree, so you will get the answer as follows. So first you will have the translation followed by the rotation with respect to y, then followed by the rotation with respect to z, and then you multiply 731 is our original number, original point with respect to NOA frame, and then you will end up getting the result, this one, which is the new PXYZ. So now if we do the so 90 degree, if you do 90 degree, you can cross check here also. Cos 90 degree is 0, and this is 0, this sin 90 degree was 1. And here we put the, to make the matrix 4 by 4. Okay. Now let's say, so initially they all are coinciding with each other. So after first transformation, which is basically the rotation about z-axis 90 degree, so you rotate about z-axis, so that's why this one will go to this direction. When you say rotate about 90 degree, means it's counterclockwise, so it goes this direction. And then you rotate about the y-axis, so basically this is your y-axis, so you rotate it counterclockwise, and so it so the A will come here, and this N will go, sorry, not N, so it will become A will be along with X and O will become along with Z. And then you finally do the translation, which is this one. So you can see here the graphically when we do the transformation, we don't follow this direction because this is the reverse order. So and then you get this translation, then you will end up getting this point P. So you can see now how to we can plot the point P as well. So basically the original point with respect to NOA, if you plot, so 7, 3, 1. So now you see where is your N. So your N is 7 in this direction. So this is 1, 2, 3, 4, 5, 6, 7. And then your A is basically 3. So you go up 3. And then O is basically 1 positive. So you go in this direction because this is the direction of positive. So you go here. So now, if we want to see, though it's a bit difficult with respect to three-dimensional measurement in a two-dimensional paper, but you can understand also the concept. The px will be now, because already it has been shifted 4 units, right? Already it has been shifted 4 units. Plus from here, there is also another 1 unit. So total px will be 4 plus 1, 5. Whereas y is going backward 3 units and then again positive 7, so it will be 4. And this is how for the z also 7 plus 3 would become 10. So this is graphically also we can show this the same result 5, 4, and 10. So this is so what the conclusion here is when we do the frame rotation, multiple rotation and multiple translation with respect to original frame of reference, which is the static one, not the moving one, then we do pre-multiplication. That means the last transformation will come first, and this is how the order will follow. Now, if we do the transformation with respect to its moving frame, then what will happen? So let's say the same point is now subjected to the same transformation, but all relative to the current moving frame as listed below. So that means it is the current moving frame, which is rotation 90 degree with respect to A axis, followed by a translation, and followed by a rotation 90 degree with respect to O axis. Then what will happen? So this is the case. It is no longer XYZ, rather O, NOA, and OA, NOA, and O axis. So you can see now here it follows exactly same as the its original transformation. So this one will come first, followed by the translation, and followed by the rotation with respect to O axis. And then if you do this, just putting the values here, and then you will get the answer. So once you have these, so you can see now the transformation is with respect to O axis, then translation, then A axis. So this will be much different, and you can see it graphically as well. It will have a different result, 0, 5, 0, 1. So you can see graphically the P will lie on the point axis Y. So that's the thing I wanted to discuss with you. So the conclusion here is when you have the transformation with respect to the moving frame, that means its own frame, then you just follow the transformation sequence to do the multiplication. You don't reverse it. So it is a post multiplication. So I hope that this video clears the rules of pre and post multiplication. If there is any question, feel free to contact me in my email at tanveers@iium.edu.my. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.